Welcome to Lecture 29 on bias and variance. Today we are going to look at another perspective that is different from the VC dimension and is coming from the angle of bias and variance. So this is the outline of today's lecture. We want to look at two parts. One is how do we go from the VC analysis to the bias and variance analysis. And we want to understand this notion of bias and variance decomposition, and how do we interpret this bias and variance. Then in the second half of the lecture, we will talk about several examples and try to understand there's a trade-off curve between the bias and variance. So to start with, let's begin our discussion using the generalization bound which we have introduced the last time. So the generalization bound says that I have a testing error compared to the training error. There will be a term called the accuracy. This accuracy is expressed in terms of the growth function mh of 2n, and this n will be the number of training samples. Mh is called the growth function, and using the Sauer's lemma, we show that the growth function can be upper bounded by a polynomial in terms of n. And this power to the polynomial is measured in terms of the VC dimension, d of VC, and that is a measure of the complexity of the model. So this is telling you one part of the story, that if you have an in-sample error and then you have certain number of training samples, this generalization bound tells you how well you can generalize to the testing case. We've also seen this trade-off curve between the in-sample error and also the model complexity. As the VC dimension grows, we understand that your out-sample error will first drop, and then it will grow as a result of the increase of the model complexity and as a result of the drop in terms of the in-sample error. So what we want to do now is try to look at this equation again and try to come up with an alternative way of trying to decompose this in-sample error and the out-sample error. So the VC dimension is one way of decomposing the in-sample error and also the out-sample error in terms of by writing the out-sample error as the in-sample error plus the accuracy. Okay, and this epsilon is also known as the penalty of the complexity of the model. Now, when we go to the bias variance decomposition, we must understand that the bias and variance decomposition is just another way of decomposing the out-sample error. It's trying to decompose the out-sample error into how well that your hypothesis set can approximate your target function, and how well can we zoom into a good hypothesis in your hypothesis set. So what do we mean by zoom? Well, what we are going to do is that we want to look at the hypothesis set, and this hypothesis set, of course, we want to compare against with a target function. The target function is there, and then you want to see how well my hypothesis set is compared to that target function. If a target function is a high-order polynomial, and then my hypothesis set is a first-order polynomial, then there will be some kind of gap between the hypothesis that you're choosing compared to the target function. So that is the first question, is how well can your hypothesis approximate your target function? The second question says that how well can we zoom in to a good edge in your hypothesis set? That means among all these hypotheses, some hypotheses will be more preferred. Why? Because according to the training set that I have, I'm going to pick certain hypotheses out of their hypothesis set, and that should give us some notion of the variation within your hypothesis set. Now, if you try to answer these two questions, you will end up having the following results. The first question will give you what we call the bias, and then the second result will give us what we call the variance. Bias is measuring how well your hypothesis set can approximate the target function, and the variance is a measure of how much variation that you have for your hypothesis inside your hypothesis set. So let's go from the VC analysis to the bias and variance analysis using a few equations. So in the VC analysis, we define the out-of-sample error as the expectation, as the probability that your target function, your final hypothesis gx, is not the same as your target function fx. Now, let's define a bad event B being the set that gx is not the same as your fx, and bad event would be either +1 or minus, either would be 1 or 0. Then we can show that the outsample error can be written as just the probability of b equals to 1. Okay, and then I can also further write it as 1 times the probability of b equals to 1, and then 0 times the probability that b equals to 0. This is just the expectation of having a bad event. So now we know that the outsample error can be written as the expectation of over all the possible samples in your population set applied to the indicator function of this event. So what we mean is that the outsample error, instead of looking at it as a probability, we can try to understand it as the expectation of certain events. This expectation is taken over all the possible x drawn from your distribution px. So now let's try to also change the error metric. In the VC analysis, we define the error to be the indicator function. Okay, so here we say that the expectation is applied to the indicator on whether the g is the same as your f. Now this expectation is a 0-1 loss, and the 0-1 loss can be changed to other types of loss. So in the bias and variance setting, we are changing the bias and the loss in the bias variance setting from the 0-1 loss to a square loss. So instead of using an indicator of whether there is a mistake or there is no mistake, I'm replacing it by a square term between your g and your f. This is called a square loss, and the square loss is good because this is a differentiable loss. And so now let's go to another notion of training sets. So we have the square loss, and then we understand it is expectation. Let's also try to understand the implication of your training sets. So in the VC analysis, when you calculate the final hypothesis, remember that the final hypothesis is actually chosen according to your training set. And so G, in principle, it should be a function of the training set D. Now, the final hypothesis depends on D. And so if you use a different D, your G will also become different. In the bias analysis, we want to define the same way. Instead of having a G, we also want to say that the G would be defined using the D. Okay, so G is defined using the specific hypothesis, using the specific training data set that you have. So it becomes G of D. So why did we skip the D in the VC analysis? It's because that the Huffington inequality is uniform applying to all kinds of distributions. Okay, so you do not need to tell me how your x is drawn from the P, because the Huffington inequality does not depend on the particular P. In other words, it doesn't depend on a particular choice of your training set D, and so that applies to any kinds of D. But that is not true in terms of the bias and variance analysis, because in the Huffington inequality, we can just bound the probability of that event using a universal bound. But in bias and variance case, you cannot write the same equation by using a one universal upper bound bounding the bias and variance. And therefore, in the bias and variance, we want to keep this idea of that G is a function of your D. Okay? If G is a function of D, then you should have some randomness in terms of your D. So, if D changes from one training set to another training set, then you want to eliminate all the possible randomness in your training set. That means you want to take an average over all the possible Ds. And to account for all the possible Ds, let's try to take the expectation over all the Ds. So in this case, in this equation, I'm going to take the expectation of all the Ds on both sides of my equation. And so now, this E out of G of D is measuring the outsample error for the particular G found using this data set D. And so the expectation of over the D says that I'm calculating the outsample error averaged over all the possible Ds. Now, the difference between the VC analysis and also the bias and variance analysis can be seen as the following. VC analysis says that I want to give you the trade-off between the worst case analysis of over all the possible Ds. So this is giving you a uniform bound over every D. The bias and variance analysis says that I want to look at the trade-off between the average analysis. Okay, so it's now the average analysis over different Ds. So you have a different collection of training sets, and then I want to take the average over all these training sets. So we can now decompose our outsample error in terms of the following equations. So to account for all the possible Ds, we can compute the expectation and define the expectation of the outsample errors. So now in this equation, you can see that we can have the expectation of the outsample error, which is the expectation taken over all the training sets. And then on the right-hand side of this equation, you have the expectation over all the X, which is used to calculate the error. And then you take the expectation of D outside to eliminate all the possible randomness in your training set D. So let's do some calculation of all these on the both sides. So let's look at the right-hand side. The right-hand side of this equation says that I am looking at the expectation of D and X on the square term. And now I can switch the order of expectation X and expectation D to get to this equation. And now I can also further expand the equation into these three terms. Now you can see that the first term is the square of the G, and the second term is 2 times G and F. The third term is just the F square. Now, if you look at the equation here, you see that I can also rewrite my G in terms of the expectation. And I'm going to define the expectation of the G in terms of this G bar. Okay, so G bar is really the average of your final hypothesis evaluated over all the possible training sets. That will give you an average final hypothesis. Okay, and so now you have for different D, you can calculate a different set of G's. And so now I'm going to calculate the average over all the possible G's. Now, if you try to also understand further that this E of D is the average over all the possible training sets. Because of the randomness in the training sets, every training set D will give you a different final hypothesis G. And so when you try to take the average over all the possible Ds, that will give you the average of the final hypothesis. Now, I'm not taking the average over, I'm not just taking the average of my data set. I'm taking the average over my G evaluated on the data set D. In other words, I have this data set. I use the data set to calculate the final hypothesis first, and then I'm averaging over all the final hypothesis. So what is the meaning of this average G bar? Well, this average G bar comes from this equation of the expectation of the G calculated using different Ds. And we define this G bar as ED on G of D. So this is what? This is the asymptotic limit of the estimate. Now, if you look at this equation here, you realize that on the right-hand side of this equation, this is the finite average of all these G evaluated at different Ds. In this case, it will be denoted as DKs. So for every DK, you have a different G. And now you're taking the average of all these G of DKs. When you calculate this finite average may or may not be part of your hypothesis set. Because why? Because you're taking the final hypothesis, you take the average. Each final hypothesis is part of your final hypothesis set, but who knows whether your average is still inside. Okay? Each GK, each G of DK is inside the final hypothesis set, but then this G bar is not necessarily inside the hypothesis set. Now let's look at the bias and variance decomposition. So let's do some additional calculation. Now we have this expectation of the E out. Now we know that the E out is also depending on the final hypothesis that you're choosing, which in turn depends on the particular data set that you use to train the final hypothesis. So we can ask what is the expectation of this term. And you can see that we can expand this equation using the following approach by just calculating the expectation of my G of D square, and then you'll have a second term and third term, and outside I will take the expectation over all the possible X. Okay, and so now I can replace the second equation, the second term here by G bar, and then I can also do a very simple trick by adding and subtracting a G bar square. And that will define me two terms. Okay, the first term is the expectation of over all the possible data sets, and then I have this G of D minus G bar. Okay, so that will give me a term. Now you can also show that why this is true. You can do a simple calculation that this is a square outside the bracket, and then you can expand this term out, and then you can move the terms around and then use the definition of your G bar, and then you can show that this is the same as what you have in front here. It would be the difference between the two square terms. Now, how about the other term? The other term is just the square, just the square between a G bar and also your fx. Okay, so you can calculate that term. And now we have defined the two terms. The first term is called the bias. Is defined as the G bar minus the f. That is measuring how far is your average hypothesis compared to the target function. So that's called a bias. All right. So this term is called a bias, and then this term is called the variance. This is called a variance because now you're measuring what? You're measuring your independent G of D, which is a random hypothesis, final hypothesis, depending on your hypothesis, depending on your training set D. And so this G of D is random. The G bar is deterministic, okay, in terms of the randomness of your training set. And so now you're taking the square and you take the expectation that is calculating the variance over the training set. So I have defined these two terms. I defined the bias term. I have also defined the variance term. And so now I want to take the expectation. Remember, outside this equation, I have an expectation. I want to take the expectation over all the X. And so, if you want to be more careful, then the bias term here is a bias of the X. So for the particular testing sample X, I will have a bias term. For particular sample X, I have a variance term. And so if I would further take the expectation of X outside, then I can define the overall bias and also the overall variance as what I'm showing you here. So now we have reached the decomposition of your outsample error in terms of the bias and also in terms of the variance. So this will give you the bias and also the variance in this equation. So the outsample error, when you take the expectation over all the possible training sets, then that will give you the expectation over the bias and variance, and then you will have a term called a bias term, a variance term. Now let's spend some time trying to interpret the meaning of bias and variance. In this decomposition, as we have shown, you have bias and variance, and the bias is measuring how close is your average function G bar compared to the target. So you look at here, this is the average, and this is your target. Now, the variance measures the uncertainty that you have around your G-bar. So how do we understand these two? First of all, you can imagine that for a collection of training sets, that will give you a different collection of different final hypotheses. That would be the different G of D's. So you can imagine that if I use this training set, I will have one particular G of D inside the circle. So one point here, and then I use another training set, I will have another point. So that will create a collection of all the possible hypotheses. And then among all these hypotheses, I can calculate the center. The center will be the average. That will be the G-bar. Now, the variance is measuring how much fluctuation that you will have from the center to each individually found final hypothesis. That would be the variance. The bias would be the measure from the center to the target function. Okay, because the target function is not necessarily inside the spore. So you can measure the distance from your center to the target function. So if the two are both small, then you have a very, very good generalization, because the outsample error is really measuring what? It was measuring one particular point from your sample and then compared to the target function. And so this decomposition using bias and variance will give you a notion of how to quantify the distance. So let's try to understand the bias and variance using this figure. So as I had described before, that the bias is measuring from the center in this diagram to the target function over here, and then you have a hypothesis set. The bias and variance, they're defined in this way. Now, if you have extremely simple H, like the case that I'm showing you here, and then inside you have a small h, and then in this case you have the variance will be very, very small. Now, if you have very, very small variance, then that is a good news. However, in this example, I'm also showing you that the bias is somewhat big, right? Because the distance between your center point and then to the target function, this is a bias term here. This bias term is big. Okay, so if you have a simple h, it is very possible that your variance is small, but then because your model set is very, very simple, then you may be able to create a very, very large bias. On the other hand, if you choose a model like this, where your hypothesis set is extremely large, where you have many different hypotheses that are coming out from your training set. So each black dot refers to one G of D. Then you can see that there will be a very, very large set of data points, and you can calculate what is the variance. The variance will be very, very large. However, since this hypothesis set is so big, think about you have an extremely highly complex hypothesis set, then of course this hypothesis is so big that it will include the target function. In that case, the target function will live inside your hypothesis set. Then of course you wouldn't have any bias problem, but then your variance will become very, very big. So the bias and variance in this example, it shows you that the bias variance is really also a very, very good alternative to the VC dimension to tell you what's happening when you have the model and also the sample complexity trade-off. And we want to look at this more carefully.